In this session, we are going to learn about the applications of Gauss law. In the previous one, we saw how if we start from Coulomb's law, we can get at the Gauss law. However, it's a fundamental law and it doesn't really need a proof. In this particular session, what we will do is, we will apply this law in specific situations and try to find answers to the questions that are asked of us. The first example that we're going to take is of this particular case. You can see on the screen we have a sphere and we have a charged ring. These ring and the spheres are such that both of them have the same radius r, and right now let's say the ring is given charge capital Q, which is spread uniformly across it, and then this ring is inserted inside the sphere like this, such that the ring passes through the center of the sphere, and simultaneously you can see from this diagram the sphere is passing through the center of the ring because both of them have the same radius. Now, the question that we have to find answer to here is, what is the total electric flux that is passing through this sphere? In order to find answer to this question, let us first draw this diagram schematically because it's fine for the visualization, but if we want to solve problems, we need to define specific conventions, and it is a good practice really to draw diagrams ourselves so that we can find minute things about those particular situations. So let's draw a diagram here. Let's say the sphere is represented like this. This is our sphere, and I'll say that the center of the sphere is O. Then this is my ring. The center of the ring is O dash. So O dash should pass through the sphere itself, right? Or rather the sphere passes through O dash. So I have O dash like this, and this is O, and in the ring I have charge, and some of the ring is inside the sphere. So the total charge in the ring is Q and it is spread uniformly. Now, what we have to find out is that what is the total electric flux that is passing through the sphere. So the electric field in the sphere would be directed something like this, and what we have to do is find out the total electric flux due to this field. So we have to find this quantity, and we know the expression for it. When expressed with the help of calculus, it becomes equal to integration of E dot ds over the entire surface. So to denote that we are integrating over the entire surface, we will use this small circular notation. And then we have also studied about the Gauss law. It says that for any enclosed surface, this one here, the sphere is a closed surface, right? So for here, we can apply this Gauss law. This law states that whenever we have to find out the total electric flux that is passing through a closed surface, it is given by the formula Qn. Qn is the enclosed charge by the sphere upon epsilon naught. We had to find this quantity. To find this, you can see in the right hand side of the expression, we have Qn, which we can find out by using some math here, and then epsilon naught is a constant. So this question is not so difficult. Let's try to find out what is the enclosed charge. To find that out, we will use these properties that we have been given. We know that this is radius r, and this is the same for the sphere as well as the ring. Also, if we take these points of intersection as A and B, then we can say that O dash A is also radius because this is the center of the ring and this particular point is on the ring. Similarly, O dash B is the radius. So what you can see is, if you consider the triangle O dash O and A, each of the sides is equal. It is equal to r, which is the radius of both the ring as well as the sphere. So what we can say is, this is an equilateral triangle, and hence all these angles, they should be 60 degrees. Well, we can make the same comment about the triangle O dash O and B. Even here, all the sides are equal to the radius, and hence all the angles have to be 60 degrees. Now let's consider the angle AO dash B. you can see that it is comprised of two angles and both of them are 60 degrees. So this total angle, I'll write it here now, angle A, O dash B, this angle is equal to 120 degrees. Now, the other reasoning that we have to employ here is, let's say this is the total segment that's inside, it's AOB. So the charge is Q in over the entire ring, and out of this ring, which subtends an angle of 360 degrees on the center O dash, the 120 degree part is inside the sphere. So if you want to find out what is the total charge that is inside the sphere, you can simply apply the unitary method and get the value of Q in as the total charge, and then we will multiply it with 120 upon 360, because 360 degrees is the total angle that the ring is making on the center O dash, and out of which 120 degrees is inside the sphere. So this gives me the right value for what is the charge that is enclosed by the sphere. And if I make these simplifications, this is 1 and this is 3, giving me the enclosed charge value as capital Q upon 3. Now you can see that the question is fully solved. What we had to find out was the value of flux, and we know that the value of flux here is Q enclosed upon epsilon naught. So Q enclosed is Q upon 3. We can simply write the value here. The answer that we are looking for is Q upon 3 epsilon naught. So I will just highlight this relation here. So this is one of the types of applications of Gauss law, wherein we have been told what is the charge distribution which is inside the surface, and then we just have to find out what is the electric flux that is passing through that surface. This was one of the simpler applications. The other category of applications is reasoning based applications. Let's take a specific example again. This time in our example, let's consider what happens in the case of a conductor. So let's say we have this block, and then this block is exposed to external electric fields. We have studied this similar situation when we were studying about the medium and the effect of medium on calculating the electric flux. We studied about dielectric constants also at that time. So what we had seen was, no matter how much electric field is here, and if the conductor is neutral to begin with, what will happen is some electrons will accumulate in this phase of the conducting block and making a negative charge in this phase, and due to which there will be a net positive charge in this phase. This negative charge and positive charge are simply a manifestation of imbalance between the number of electrons and number of protons here. Now, as a result of this, I already know that in a conductor, the electric field inside its volume is always 0, because had there been any electric field, what will happen is, due to that electric field, the electron that is residing here, it will move in the left phase. Similarly, if the electron resides here and moves there, what will happen is the induced electric field will keep on increasing, and it will increase in such an extent that the induced electric field will become equal to the external electric field, and the resultant electric field at any point inside here will become equal to 0. So based on that logic, let's say I take any arbitrary surface. Let's say this is a closed surface. From now on, whenever we take these closed surfaces, in order to apply the Gauss law, we will call them by a special name known as Gaussian surfaces. So whenever we say Gaussian surface, we will know that we're talking about applying the Gauss law in a particular situation to know more about it. So this is any enclosed surface inside the volume for now, and then we know that at any point the electric field in this surface is 0, because at any point inside this block the electric field has to be 0. Then what is the flux that is passing through this surface? Flux is nothing but E dot ds. E is always 0. So 0 dot ds which if you integrate will get you 0. Now using this logic, we can safely say that if we apply the Gauss law, then we know that electric flux in a closed surface is equal to Q in upon epsilon naught. So epsilon naught is a positive constant, it cannot be 0. It means that the enclosed key results or key interpretations that Gauss law has given us. This says that in a conductor there can be no charge residing inside the volume of it. All the charges have to appear in the outer surface, not even in the internal surface. Why? Because had it been appearing here, we could have taken this particular Gaussian surface like this, and then we would say that since there is charge enclosed by this surface, then the electric flux should not be 0. But we know that the electric field at every point on the surface is 0, and hence the electric flux has to be 0. Applying that logic, this is one of the very interesting results that we have obtained, that charge enclosed inside the conducting block is always 0. Even if you inject some charge to this conducting block, let's say it was neutral to begin with and there was no electric field also. Let's begin with this particular situation. And then by some scheme, let's say you induce some charge in the internal volume of this conductor. Let's say you induce charge Q here. Then what will happen is this charge Q will rush to the edges or in the outer surfaces, and it will align itself in a way that there is no charge left in the conducting volume, and hence whenever we take any Gaussian surface, the electron. So let's say we have this cavity, or rather a spherical shell, wherein this is material. I'll denote the material like this, and this part is free. It might be a vacuum, it could be air or whatever. We're not concerned about it right now. Now, if we subject it to the external electric field, what will happen? Now it has two surfaces, right? There is this outer surface and we also have an inner surface. So will the charges be aligned in such a way that minus charge comes here and plus charge here? Well, the answer to this question can be only found out by Gauss law. Let's try to apply the law here. For this Gaussian surface, this field E naught is acting upon every point of this surface, and we also know that the total electric field at any point, because it is also a part of the conducting volume, it has to be 0, right? So if it has to be 0, then what should be the total charge enclosed by this surface? The total charge enclosed will be given by the Gauss law, which says E dot ds equals to 0, or this is also equal to Q in upon epsilon naught. Now, this is an interesting anomaly. What you see here is, even though this electric field E naught is acting here, but what you see is that the total electric field at every point has to be 0. So there should be some induced electric field also. Now we are not concerned about how this induced electric field is coming into play. What we have to see is, if E is the electric field, the general electric field at any particular point on this particular surface, we can see that this law always holds true. And this means that the total charge that is enclosed in this surface, which could have appeared in this inner surface of the spherical cavity, that has to be 0. So this is the interesting result that we obtain, that even for this case, the enclosed charge becomes equal to 0. Then you might ask, how does the charge redistribute itself when such a case is presented, where we have an external electric field and a spherical cavity? We will do this analysis in the later session because we need some concepts about the earthing and redistribution of charges. Let's say now we make this electric field as 0. We are modifying this situation even further, but this time I am placing a charge small q in the center of this spherical cavity. What happens now? If you observe this particular Gaussian surface again, you know that it is the part of the conducting volume, the conductor volume, hence the electric field at every point is going to be 0 for sure. So if the electric field at every point is 0, it means that the total charge enclosed must also be 0. However, what we are seeing is that there is a charge q that is kept at the center of the spherical cavity. Hence, what happens here is, because there are a lot of free electrons in this conductor, these free electrons redistribute themselves. Some of the electrons appear in the inner surface this time like this, and the magnitude of the free electrons or the charge that has appeared here should be equal to q itself, but their sign should be opposite. So we have a minus q charge in the inner surface of the cavity. Notice that the cavity as a whole is neutral. The cavity hasn't been provided any charge, and if minus q charge is coming in the inner surface, then plus q charge should accumulate in the outer surface. So this is a very interesting phenomena that we have observed, that whenever we have a conducting cavity, if any charge is kept inside the cavity or the free space, then the charges in the spherical cavity, they kind of realign themselves. If it were neutral to begin with, the inner surface will get an equal and opposite charge, and the outer surface get the equal charge and also same in sign. So if we keep a charge q here, then minus q comes here and plus q comes here. It's like a redistribution that has happened, and this redistribution will always satisfy this particular fact that the electric field inside the conducting volume is always 0. So this is one of the very interesting results due to the Gauss law. Now next, what we are going to do is deal with a certain class of problems wherein we will be interested in finding out the electric field, wherein what we are given is, we are said that, let's say this is the charge distribution. Now can you find out what will the electric field look like due to this particular charge distribution? We will find out this that only in specific cases, that is when the charge distribution is kind of symmetric, we are able to solve this question, because in that case this particular expression here, the left hand side, which says integration of E dot ds, this expression simplifies and we are able to solve for electric field with the help of this equation or the Gauss law. We will take up those cases in the next session.